All right, 3 o'clock, so I gotta start talking. There's more people in this class than there was in the noon class.
Oh, wow.
Believe it or not.
Mm-hmm.
What's that? Did everyone, is there something going on?
So everyone's gone.
Not many people have dropped. But
That's weird.
yeah.
It's not
At least I haven't checked. A lot of people listen to me online. They don't come to class and they look at the lecture archive, which you're welcome to do. So if that's what you're doing at home, cheers to you.
coming.
But thanks for coming, guys, I guess. Actually, today we're going to finish up Chapter 7, going to Chapter 8, and nothing that we talk about today is on the next test. So, next test is November 7th. So, we got some time. We'll have a review day in there. But it's also, I was looking at the schedule, it's getting kind of scary because we're running out of time, believe it or not. Because we miss a day for Veterans Day, and we also, well, I guess Thanksgiving, it's a regular week for us. But yeah, it's getting scarily towards the end of the semester. I guess it's not even Halloween yet. Anyways, anybody have any questions about anything before we start? So I mentioned about orbital shapes, and this is where I left off, is talking about the orbitals, and look at the s orbital, the 1s orbital especially, that it's the electron is, where is the electron? It's in all these places at once. It just occupies a space. We're unsure of its position or momentum. That changes if we probe it, of course. But this is what the electron density is like for the 1s electron. It has a maximum of about 52.9 picometers away from the nucleus for the hydrogen atom. And so the y-axis here is the probability, x-axis is distance. But there is some density at the center, which means there is electron density inside the nucleus of the atom. So, it's most pronounced for the 1s orbital, but this is the reason why different isotopes, so same number of protons, different number of neutrons, atomic size is slightly different with that, so the energy levels of the electrons change ever so slightly for them. They're similar, not the same. And this is more important when we talk about bonding, but pretty soon we'll talk about the sign of wave functions. So imagine that if I take like a rope and I attach it to the wall and I can spin it around and I can make kind of like a ropey pattern like that. If I do it really, really hard, I can get 2 of these. If I do it really, really hard, I can go to 4 of them like it's pictured up here. So the sign of the wave functions, the upper one is positive, the bottom one is negative. That's important for bonding, like I said. But the thing to note is that you have these areas of zero density, and those are called nodes. And well, it's nodes in the like the rope example. The same thing with electrons. There's nodes. So the 1s has no node. The 2s though has a node there, and the 3s has 2 nodes, and the nodes are areas of no electron density, zero density. And if you notice the nodes, it's also n minus 1. So the 1s has 0 nodes, the 2s has 1 node, 3s has 2 nodes. And something to note with these functions here, you see here the total probability versus distance. There's a little hump here, and then there's 2 humps in there. Later on today, we're going to talk about something called penetration. And so when an electron looks at the rest of the nucleus, it's shielded. The nucleus of the atom is shielded by the other inner electrons. But an s orbital can penetrate through that because of this stuff here and here. So whereas the s penetrates much more than the p does, for instance. So we'll talk about that later on today. And these are just the orbital shapes. So here is the 2p function. And there is a node, it's at the origin. So the two P's do have nodes, and the node is right at the origin, so there's much less density in the nucleus for the P's. And remember with L equals 1, M sub L is minus 1, 0, and 1. These are just the M sub L, one's minus 1, 1, 0, one's 1. It doesn't matter which one is which, they're all the same. They're just oriented differently. And the sign of the wave function here, so on the x-axis here, the positive x-axis is positive, negative is negative. Like I said, that sign becomes important later when we talk about bonding in chapter 10. And the P's are just perpendicular to each other. P doesn't mean perpendicular, means principal. Here are the D's, and the D's have the signs as shown. There are 5 D's, and these are the 3D, the ones pictured. So if you have an axis, you have along a plane. So if you see here the XYZ, you have the DYZ. DYZ is a flat plane, like the wall, and not along the axes, but along the diagonals is where the wave function is, where the electron density is. I guess same thing. And there's 3 of them: the DYZ, the DXY, and then the DXZ, like these orientations. So flat, this way, and all along like a clover leaf along the in between the axes. And you have 2 that are along the axes, the x squared minus y squared and the dz squared. Now these 2 orbitals right there, those are the ones that typically do bonding for metals. Along these, you can have bonding alongside the axes from those. And here are the f orbitals, or the 4 f orbitals. They just look kind of cool. They're like balloons, I think. They're even funkier than the 3D. So, and atoms are basically spherical. Why is that? So let me show you. Here's an s orbital. That's just, run like that. Maybe I should change the color. Put something bright yellow. So then you can have the p orbitals. Here's one. There's one there, and then along there. The d orbitals. So there's one along this plane. There's this plane there. Then the flat. Like that. Then you have the x squared, y squared, and then the dz squared in a donut. So if you see how I overlaid all those, that's why atoms are kind of spherical. I mean, the electron density is not a perfect sphere, except for maybe like a hydrogen atom or a helium atom. It's pretty spherical. But all the other ones, well, I guess lithium would be that way too, and beryllium. But then when you get to the p orbitals, these start to have a break in symmetry. But atoms are basically spherical. But yeah, we're done there. Anybody have any questions with that? This is more enrichment. It's not really testable. But I always thought it was cool, the pictures of the orbitals. Okay, now we're on to chapter 8. Talking about periodic properties. And much of this I've already spoken about. So defining the orbitals for angular momentum quantum number L. When L is 0, it's an s orbital. 1, it's a p orbital. 2, it's a d. 3, it's an f. And we're going to do what's called the Aufbau principle. It's called the building. That's German for building up, because there's just a lot of chemistry. It was invented in Germany. Germany put a lot of money into chemistry. So start with hydrogen, the simplest. One proton, 1 electron. And we have 1 electron in the 1s orbital. And we just denote it there as such. And then helium has 2 electrons, and the difference between these 2 electrons is that one's spin up and one's spin down. They cannot be both spin up or spin down because of the Pauli exclusion principle, which we talked before, that no 2 fermions within the same atom can have the same set of quantum numbers. And that's the reason why matter has structure. Otherwise, everything would just be the lowest orbital. That's why we have repulsion, and that's why matter has structure, and we can't occupy. Well, electrons can, but we bulk-wise cannot occupy the same space at the same time. So, and let me talk about hydrogen atoms. For hydrogen or hydrogen-like, meaning 1 electron, all of the same principal quantum numbers have the same energy. They're called degenerate. So like the 2s, 2p, same energy. 3s, 3p, 3d, all same energy. That means that we use the word degenerate for that. Degenerate kind of has a negative connotation as well. Like, actually, it can be a compliment. Like, if I said, you students are a bunch of degenerates, you're all doing great. That means you're all the same. Degenerate means you're all the same. Usually it means like, oh, you kids are all the same, into crime and Pokemon Go and that kind of stuff. When I was your age, we had Game Boys and Slinkies. So, anyways, but what about atoms with more than one electron? You have two effects. The electronic field can cause the Stark effect, and then the magnetic field can cause the Zeeman effect. For electrons in an atom, the Zeeman effect is more pronounced. And I don't know if I show how much of a nerd I am or lack thereof. When I was watching Iron Man, he says Tony Stark, I thought of the Stark effect. I was like, oh, just like the electronic field affecting energy levels. This is more for chemical reactions and promoting chemical reactions. Doesn't really affect, it does, but it doesn't affect the atomic electron orbital energies from other electrons. Something outside can affect it. So if you have a potassium atom, for instance, next to an iron atom, that affects the chemistry of catalysis, for instance. But not so much effect here. Zeeman effect, very important. It causes splitting of the energy levels, which I'll show you in a second. And a couple things. So Coulomb's law, I'll zoom in on this. Why do things bond? Why do we have electrons bonding to positive protons? Because of the Coulombic force, and it's right there. This is not a physics class, but I didn't put the vector. There's a vector here. Radius has a vector. The force is a constant. Charge of one, charge of the other over the distance squared. This is going to become important when we talk about some of the periodic trends, though. And then shielding, I mentioned was shielding. So how shielding works, and I'll show you something soon. So lithium, for instance, lithium has 3 electrons. 2 electrons in the 1s orbital, 1 in the 2s orbital. So the 2s orbital, so if I'm lithium and here's my positive nucleus center. This electron out here, there are 2 electrons here that shield this outer electron. So this outer electron effectively only sees a +1 charge instead of a +3 charge. And that is known as shielding, but the penetration, there is some penetration there, and it's not a completely effective shield because of that penetration of the 2s orbital. And here are the S penetration is much more pronounced than the P and the D. Okay, so I mentioned the Zeeman effect, that when you have orbital energies that have other electrons around, they change their energy levels. This is what it looks like. You don't have to memorize this. Any stuff like this will be given to you. And let me show you what's known as the Aufbau principle, the building up principle. So this is what hydrogen is like. Here's helium, spin up, spin down. Lithium's ground state. When I say ground state, so that's a ground state for lithium. This would be an excited state of lithium because it's not the lowest energy level. This is the lowest energy level for lithium, beryllium, then boron. Now when you go to carbon, do you put carbon here like this, or do you put it up like this? You put them up like I've just shown, like just now. This is known as Hund's rule. When you add electrons for degenerate orbitals, they add one at a time and with parallel spins. So now here is nitrogen. Then for oxygen, they pair up fluorine, neon, like so. So some other points. Let me go back to this. So here, now let me add an electron. Actually, I'll even go back to lithium. So you look at lithium with one unpaired electron. This is known, this configuration is known as paramagnetic. So lithium as an atom has a magnetic field, like an active magnetic field. That's known as being paramagnetic. Beryllium has one more electron, it's paired up. Beryllium is diamagnetic. It has no external magnetic field. So, and then boron, paramagnetic, carbon, paramagnetic, nitrogen, extremely paramagnetic, oxygen, a little less, but still, fluorine, paramagnetic, neon, diamagnetic. Now, a common misconception, the paramagnetic diamagnetic has nothing to do with chemical reactivity. So fluorine has one less. There's fluorine. Fluorine is paramagnetic. It's extremely reactive. Gold is paramagnetic. It's extremely unreactive. Neon, here's neon. Neon is diamagnetic. It's very unreactive. Calcium as an element is diamagnetic. It's extremely reactive. So there is no correlation between, or causality, I should say, between paramagnetic and diamagnetic and reactivity. It only has to do with magnetic properties of the atom. And the other thing that's confusing, the magnetic properties of the atoms do not necessarily translate into bulk paramagnetism or ferromagnetism. So I'll give you an example. This here is aluminum's electronic configuration. So aluminum as an atom is paramagnetic. But if you put a magnet up to aluminum, it doesn't stick. So the bulk material does not mean the same as the atom in this case. Okay, let me keep on going. Let me note something else. So here are the 3 P's. So adding up like this. So you add parallel spins first. And notice something, the 4s is lower in energy than the 3 D's. So the 4s gets populated first with this. And soon we'll talk about valence electrons. Valence electrons means outer electrons. The outer electrons are the ones that have the highest n, the highest principal quantum number. So as written here, the valence electrons are these 2 4s's, but we'll talk more about that later. So this is kind of just what I said with this building up principle. Here's lithium, there's beryllium with one more, and then boron, carbon, nitrogen, you add 1 electron at a time, and with parallel spins, we typically go spin up just because we're very positive in chemistry. They can be spin down, doesn't really matter. But then when you pair them up, the spin is opposite. Okay. So let's see if you follow this. What is the ground electron configuration for sodium? And sodium just has 1 more electron than neon, which is listed up there. Let's see if you're following me. How many think it's A? How many think it's B? How many think it's C? How many think it's D? So is anybody confused by anything? This is, the first class, they didn't want to vote, but then when I went around and talked to everybody understood it. Is that how you guys are feeling too? No, you're not. Okay. You're confused?
Yeah. So in the answers, it says like 1 is 2. Does that mean there's 2 like?
That means there's 2 electrons. The superscript, this means that there are how many electrons? Oh, I'm sorry, I didn't explain that. So 1s2, that means there's 2 electrons in the first s. 2s2, 2 electrons in the second s. And 2p7, that means that there's 7 electrons in the 2p orbitals. So this one's actually wrong. It can't be that one because only 2 electrons can be in each orbital, and there's 3 p orbitals. So A is false. there can only be 6 electrons in a p. And something else is false. Which one is it? C is false, yeah. You can only have 2. That's 3s11. So your choice is between B and D, and they're both possible. So D, because you have 2s1, so it's 1 electron there, and then 2 electrons in a higher orbital. This means it's an excited state. So the ground lowest energy is this one. Does that make sense?
Yes.
Questions, anyone? Okay. So maybe you've seen this before. This is Lewis dot structures. And Lewis, he thought that, I know this is a rectangular prism, but he thought atoms were like cubes. And cubes have 8 corners. Okay, so 4 up top, 4 on the bottom. And he thought that atoms try to be like full cubes, and that's why he said, oh, then this is the octet rule. So atoms tend to bond to have 8 electrons, just like the noble gases. So, like I said, he thought they were cubes. He was right about the number 8. He was wrong about them being cubes. So he was right, but for the wrong reasons, interestingly enough. But he came up with the idea of these electrons being dots. Electrons are not dots. They're this fuzzy cloud. Okay, but it helps illustrate some points, and we use Lewis theory quite a bit. So, even though it's fundamentally wrong. So, some terms, valence electrons are outer electrons, and those are the only ones you see. And core electrons are the ones on the inside. Like, does anybody know what color my socks are? They're not white, but they're gray. But you can't tell because there's a desk, and I'm wearing shoes, right? I'm wearing shoes, and I have long trousers on. Everything is being covered. You can't tell what I'm wearing on the inside. You can only see on the surface. I mean, you can see I have a white undershirt on, but that's because it's if I buttoned up, all the way, like, now what color is my shirt? You couldn't tell because it's blocking. So clothing works the same way as electrons. So you can only see the outer clothing, or at least in theory. Of course, I know straps stick out here and there. But think of it kind of like clothing. Think of hydrogen like someone wearing a one-piece bathing suit. And then helium with 2 electrons, so hydrogen, 1 electron, 1 item of clothing, nothing else. Helium, 2 pieces, it's like a woman wearing a bikini kind of thing. So there's helium. And then lithium would be like a woman wearing a bikini, but wearing a sundress that covers the bikini, that you can't tell what color or shape the bikini is because the sundress covers it completely and perfectly. So then lithium would be like, same thing, bikini underneath, sundress, and a hat. So as you add more and more clothing, you can see the outer ones, cannot see the inside ones. So what matters though, so atoms are very superficial. They only care about what's on the outside. They don't care what's on the inside. They only care about what they can see on the outside. And so boron and aluminum, they only care that there's 3 on the outside, even though aluminum has 10 more electrons. And that is why the chemistries for items in the periodic table in the rows, in the columns, they're very similar because they have the same number, they have the same outside electronic configuration. So it makes the chemistry very, very similar. And here are some things. So, how are we going to start? Questions with this? Okay. All right. Identify the electronic configuration for germanium. Germanium is right here under silicon. Identify the valence electrons. I guess I'm jumping ahead. You can tell from the periodic table, and here is germanium right here. So these right here are the s orbitals. These are the p orbitals. These are the d orbitals. These are the f orbitals. And so germanium is going to be, it's going to be 1s squared for the 2 electrons. So 2s squared. So that's, I'll say it here. 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s squared, 3d10, 4p1, 2. So when I said here, 2p6, 3s squared, 3p6, 4s squared, 3d10, 4p2. That is germanium's electronic configuration. And the valence electrons are the 4s. There's only 4 valence. The Ds, because they're a lower n, our n is the 3, that's considered to be core. So the valence are the highest n only. So there's only 4 electrons, 2 in the 4s and 2 in the 4p. So there are still 4 valence in germanium. Is this making sense? There's a shortcut for this as well. You can look at this and you can say that's the electron configuration for argon and leave it like that, and then write 4s squared 3d10 4p2. So you can only do that for the noble gases. So noble gas configurations, you can't put in zinc 4p2, for instance. That's not considered proper. So, and this is how you use the, and I just did this, use the periodic table, and then what is the electronic configuration of selenium? Selenium being right there, and selenium's is argon, like I said, 4s2. So you can do that for the noble gases. You can go to a you can jump on the noble gas configuration. Argon's configuration, 4s2, 3d10, 4p, 1, 2, 3, and 4. So there are exceptions now, mind you. Problem with this, there are exceptions. You don't have to know the exceptions. Copper, silver, and gold are exceptions. For instance, you can see that one of the 4s squared, it's a 4s1 and it's promoted to the Ds. So you don't have to know the exceptions. You just have to know the general concept. Any questions so far? Okay. So let's see if you're following. What is the electronic configuration for phosphorus? Phosphorus, I should tell you, it's right here. How many think it's A? How many think it's B? How many think it's C? How many think it's D? Okay, it's not D because the P has 2 and the S has 3. So that's backwards. So it's not D. And you can only use a noble gas configuration. It's not C, right? You can't do magnesium. So it's either A or B. So yes, it's B because A, that's an excited state because the ground configuration is going to be all the electrons in the 2 in the 2s, I'm sorry, the 2 in the 3s, and then the remaining 3 in the p's. Is that making sense? Okay. And here is the power of the quantum mechanical model. The number of valence electrons dictates properties. So sometimes the columns are referred to as families, and here's a picture of my family, although this picture's taken about 10 years ago. So you can see I had more hair back then. And of course I'm on the right, and there's my brother on the left, and my 3 sisters in the middle, and then my parents in the front there. But you can see that we're all related, at least my siblings and I. We're all big and blonde. So I got those good Neanderthal genes from mom and dad. So, and this is a picture. Here's John Allen Ferguson Sr. on the right, my father, my brother John Jr., and then there's John III on the left, holding copper, silver, and gold. And this is an example of copper, silver, gold is an example of a chemical family. And you're like, wait a second, they look nothing alike. So gold is yellow, silver is the same color as most metals, and copper is yellow. Or not yellow, it's a red. Why is it, how are these the same? They're similar because they're unreactive. So gold's very unreactive, silver is slightly more reactive, copper is pretty unreactive, but not as unreactive as silver or gold. Of course, gold is, of the 3, gold is the most unreactive. Also, they have some similar properties too. They all conduct electricity pretty well. So we use copper wiring in houses. Why don't we use aluminum? Because it's cheaper, because copper is less resistive, it causes fewer fires. So you can put more electricity in the wires in a house. And it's less likely to catch on fire. And they're also all expensive, right? So they have that in common. So, and also with the periodic table, there's trends in terms of charges of things. So the alkalis tend to be +1, alkaline earths tend to be +2. Why? Because alkalis have 1 valence electron, it's easy to rip off. Alkaline earths have 2, easy to rip off. And then the halogens, fluorine, chlorine, bromine, iodine, they need 1 electron, so they all tend to form -1 ions. Oxygen family, or group 6A, tends to get 2 electrons, and so on. So now we're going to talk about the various periodic trends. The first one is atomic radius. So, but I should back up. Anybody have any questions so far? Following? Okay. Atomic radius, and the trend is the further left you are, the bigger you are, and the further down you are, the bigger you are. Okay, so the reason for that is because of the atomic center. So let's look at hydrogen and helium. So hydrogen, first element, +1 center, 1 electron. Helium, +2 center. So what's going to happen? Hydrogen, the electron here is like, okay, +1 center, but then helium has a +2 center. There's not any shielding, so what happens to the electron cloud with a +2? It shrinks. So the electron cloud shrinks, and helium happens to be the smallest atom. Not hydrogen, helium is the smallest atom. And lithium, what happens to lithium? Well, it's a +1, it's a +3 center, but it's shielded by the 2 inner electrons. So lithium, lithium's kind of fat. Lithium is a big buttery atom. Lithium is not very dense at all. So lithium is very undense, it's very light. So that's one of the reasons why we use lithium-ion batteries. It's because they're light. So, and they pack a big punch. You ever picked up a car battery before, a lead-acid battery? They're really heavy. That's why we use lead-acid in cars, because we can drive a car. So we put lithium-ion in our cell phones and iPads because it's light. They're a lot easier to carry. Okay, so lithium's big, +1 center. Beryllium, electron cloud shrinks. Boron, shrink, +3 center. Carbon, +4. Nitrogen, +5. Oxygen, +6. Fluorine, +7. And neon. Neon's a really tiny atom with the +8 center. So electron cloud, as you're going over, it shrinks down. And I'm going to talk about a couple other trends. The next trend I'm going to talk about is ionization energy. And ionization energy, that's the energy it takes to rip off an electron. So what do you think? Is it easy to rip off an electron? A really big atom, look at lithium, big atom with a huge electron cloud with a +1 center. Is that easy to rip off an electron there? Or what about neon with a +8 center with a really tight and tiny atom? So which one is it easier to rip off? The lithium. With a big atom, the electron cloud is further away, much greater distance to the nucleus, and a +1 center. So yeah, the electron just can fly off really easily. Then neon, with a tiny, tiny atom, with a very positive center, it's really hard to rip off that electron. And there's also, as we go down, so for atomic size, so lithium, +1 center, and on the 2s orbital, then you have sodium, +1 center, 3s orbital. 3s is further away, so sodium is even bigger atom. Potassium, even bigger. Rubidium, even bigger. So going down the periodic table, you just add another shell, and they get bigger. So likewise, going down the periodic table, the same positive center, bigger atom, it's easier to rip off an electron. That's the ionization energy. The last thing, it's not really taught until next chapter, but electronegativity. Electronegativity is the ability of an atom to draw electron density to itself. Like, have you ever gone to a party? I've never been to Front Street on Halloween. I don't think I'm going to make it this year. Have you guys ever been to Front Street on Halloween? You ever notice that sometimes there's like a really attractive person in a revealing costume, and then like people just kind of drawn to that person? There's like this draw. That's same thing happens to atoms and electrons, but the most drawing, the prettiest atom for that is fluorine. Fluorine has a +7 center, and it's a tiny atom. Electrons are drawn towards that. So if say you have a hydrogen bonding with a fluorine, what happens is that the fluorine gathers up a lot of electron density and hydrogen gets a little bit. The electron is drawn towards the fluorine. And that ability to draw electrons to itself is known as electronegativity. And we'll talk about that next chapter, but it's related to this stuff. That's why I'm bringing it up now. Why fluorine? Why not helium or neon? Because helium and neon, they're already stable. They don't really bond, and so they're not very good at drawing electrons to themselves because they don't care. They're non-bonding. Okay, so let's go back to the size trend. The size trend is furthest to the left, the biggest, and furthest down is the biggest. And here's a chart showing that here, that you have the alkalis are the biggest, and then the noble gases are the smallest. And the reason why is the effective nuclear charge. And also something to note, there are, for the transition metals, that this is not a smooth transition for them. It's a general trend, it's not a completely smooth trend. Okay, so let's look at this. Atomic sizes. On the basis of periodic trends, which one is bigger? So carbon or fluorine. So we have carbon or fluorine. Carbon is further to the left, so it's carbon. So questions with this one? Carbon or germanium. Germanium is underneath carbon, therefore it's the one that's bigger. Questions with this? Nitrogen or aluminum. Well, aluminum is lower than it, so it's bigger, and it's furthest to the left, so it's bigger, so aluminum is definitely the bigger atom by 2 rules. And then what about aluminum and germanium? Well, aluminum is further to the left, it's bigger, so germanium is further down, it should be bigger, so we have 2 conflicting rules, so we have no idea. We have to look at data, and which one is bigger, aluminum or germanium? Aluminum is bigger. So in this case, aluminum happens to be bigger, but you have no way of knowing. So you won't be asked an ambiguous question like this. Everything has a logical answer. And, okay. I've already mentioned these 2 things, diamagnetic and paramagnetic, nothing to do with electronegativity or reactivity. So the ability to draw electrons and reactivity, nothing to do with that. That's just a atomic only property. Okay, so, and electrons are taken from the highest end first. So let me illustrate that now. Write the electronic configuration for each ion and determine whether it's diamagnetic or paramagnetic. So aluminum, see here, aluminum is right here. So aluminum is going to be neons. I'm going to write the whole thing out for aluminum though. So it's going to be 1s squared, 2s squared, 2p6, 3s squared, 3p1. That's aluminum. So plain old aluminum, 1s squared, 2s squared, 2p6, 3s squared, 3p1. So let me do the ion. So this is aluminum. Aluminum plus 3 loses electrons from the highest end. So it's going to be 1s squared, 2s squared, 2p6. And this is just for emphasis. 3s 0, 3p 0. Has those electrons taken from the highest end. And if you look at the electronic configuration, it's going to be like this. Everything is paired, therefore this is diamagnetic. Does this make sense? Okay, let me look at sulfur. Sulfur is, I'm just going to go, it's neons configuration, 3s squared, 3p4. This is sulfur, and let me show you the chart. So aluminum was 3p1, 2, 3, 4 for sulfur. And when you, this one here, you add 2 electrons. Well, this one you subtract 3 electrons. You add 2 electrons, and you get neon 3s squared, 3p6, and similar is diamagnetic. So iron on the other hand, it's going to be, actually I should use a different color. I'll use green for iron. Iron's electronic configuration, 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s squared, 3d6. So where am I getting that from? I can read it from the periodic table, of course. But, so 1s squared, 2s squared, 3p6, 3s squared, 3p6, 4s squared, 3d, 1, 2, 3, 4, 5, 6. 3d6. Counting down. Come on, zoom out. There we go. So that's where I got that. And it's, you lose 3 electrons. So it's going to be the same thing. This, of course, this is argon's configuration. It's going to be argon's configuration, 4s squared, 3d6, and minus 3 electrons for argon, 4s 0, 3d5. So removing the electrons from the highest end, 4 is bigger than 3. Electrons are removed from there first. And there are 5 d electrons, 5 orbitals, 5 electrons, all parallel. And because of this, iron plus 3 is very paramagnetic. Actually, iron is one of the few materials at this temperature that is also ferromagnetic. You can use the words ferromagnetic, Fe for ferrum for iron. So, And there's a mineral called magnetite that is made from iron oxide, iron plus 3. Okay, so the point of this, which is to learn how to write the configuration, which we've already done, but then the electrons are ripped from the highest end first, and then unpaired electrons are paramagnetic, all paired electrons are diamagnetic. And I was only going to do with the bulk outside, I'm sorry, with the electron, with the atomic magnetic properties only. So, questions with this so far? Okay. Now, this is a concept. I remember I first taught this, and I asked a question on the test. 2/3 of the class got it wrong. So then I told everybody I was going to test them on it, and then 1/3 of the class got it wrong. And I'm hoping that no one will get any of these questions wrong. This is a good class. You guys are doing very well. So hopefully we'll get 100%. 100% in the positive direction. These are known as isoelectronic atoms and or ions. So isoelectronic, iso means same. Isoelectronic, same electrons. So if you look at these, sulfide, chloride, argon, potassium plus 1, calcium plus 2, these all have 18 electrons. So isoelectronic, same electrons. Sulfur has 16 protons, chloride has 17 protons, argon 18, potassium 19, calcium 20. Which one is the biggest ion? Which one is the smallest? Well, the smallest one is going to the one that has the most positive center. So calcium plus 2, they all have 18 electrons, has 20 protons. It's the smallest ion because it draws in those 20 plus charges, draws in the electron cloud. Sulfide, on the other hand, has only 16 protons, so it's really big. So this tells you what happens to atoms as you add and remove electrons from them. So if you have an atom and you add electron density to it, what happens to the atom? It gets big. So electrons are negatively charged, they're kind of diffuse. So adding electrons to an atom and or ion makes it bigger. So it starts to blow up. What happens if you rip electrons off? It shrinks. So hopefully you can hear the sound effects at home. So when you're comparing size, this is what you do. So sulfur or sulfide, which one is bigger? It's the one that has more electrons. So same elements. Sulfide has extra electrons, therefore it's bigger. Same thing with calcium. Which one's calcium or calcium plus 2 ion? Calcium has more electrons. It's the bigger one. Now we look at bromide and krypton. These are isoelectronic. So if we go up to, so here is bromine, here's krypton. They both have 36 electrons. The difference is bromide has 35 protons, krypton has 36. So since bromide has one fewer positive charge, it's the bigger ion. So, questions with this? Is making sense? That if you have the same number of electrons, the ion or atom with the most protons will be the smallest, and the least will be the biggest. Okay. And I mentioned first ionization energy already, but the trend of this is opposite, directly opposite of the size. So going to the right is bigger, and going up is bigger. And what is the ionization energy? That's the amount of energy it takes to rip off an electron. And so the more bound an electron is, the more energy it takes to rip it off. Think about relationships. It works kind of the same way. You could probably say, someone who's loosely affiliated with someone, like say that you have a Tinder match with someone and then the person moves away. And you've never met. And I said, all right, if I give you $100, would you agree to unmatch that person and never speak to him or her again? You'd be like, okay. What if it was like your partner for like 6 months? You're like, $100? No way. Like, how about 1 million? All right, fine. You can be, with a little bit of money, you can do things. Same thing with electrons. You give electrons a little bit of energy, they're like, I'm out of this atom. I'm leaving. So, but the more energy it takes, the more bound the electron is to that atomic center. So if you look here in the bottom left, cesium here with 376 kilojoules per mole, not very bound. Its electrons are like, all right, you give me a little bit of energy, I'm out of here. I'm flying. I'm gone. Then helium with 2,372, that's also the highest first ionization energy. It's really hard to rip off those electrons. Electrons are like, you know what? I'm really liking this +2 center with the smallest atom. I really like that. And same with neon. I really like this +8 center and this really tiny atom. I'm just going to, you have to give me more energy to escape this. So, does that make sense? Same trend, but opposite of size. Now, mind you, of course, what would my class be unless I told you there's an exception to the rule? There is a few exceptions. If you look here with nitrogen and oxygen, there's an exception there. And the exception continues up into to antimony, so phosphorus and sulfur, arsenic and selenium. It breaks for antimony and tellurium and bismuth and polonium. So, and why is there that exception? It's because oxygen here, it turns out it's easier to rip off the electron off of oxygen than that one on nitrogen because of the pairing of that. And it's not a smooth trend either. It works for some of the elements and not all. But chemistry, though, is an observational science. We only can report back what we observe. So these are trends. They're not perfect trends. Okay, but let's talk about the ones that we can predict and apply the logic. On the basis of periodic trends, determine which element each pair has a higher first ionization energy. So for aluminum or sulfur, sulfur is to the right, therefore it's sulfur. It's higher. So arsenic or antimony, here's arsenic, here's antimony. Arsenic is higher, so that means it's got a stronger first ionization energy. Nitrogen or silicon. Nitrogen is further to the right and it's further up. It is definitely nitrogen. And then oxygen or chlorine. Oxygen is further up, so it should be higher. Chlorine is further right, so it should be higher. You have no idea. That's ambiguous. Which one is it? It's oxygen. But you wouldn't know that unless you had the data. You can see the data up here. Right? So oxygen is 1314, chlorine is 1251. So, but like I said, you cannot tell that from the periodic trends. I do not ask ambiguous questions on the test, by the way. So, because I think that's mean. I guess it wouldn't be mean, but it's just, you're having a hard enough time getting this concepts right now. Why make it even more difficult on you? Okay, so then 8C. So does this mean you can have a periodic trend for everything? Absolutely not. Electron affinity. So if you add electrons to things, sometimes they release energy. The amount of energy atoms release when electrons are added, that's known as the electron affinity. Sometimes it's positive, sometimes it's negative. And there is absolutely no smooth trend. So even when you wouldn't expect it, so xenon has a pretty high electron affinity. You add electrons to xenon, it releases energy. So, and then it reacts and it gets rid of it right away. So it goes back to being xenon. So this makes absolutely, which kind of makes no sense in our chemistry world, but there's no trend. There's absolutely no trend, so we can't trend this. The book talks about this. I don't like this trend. but this is called metallic character. And the metallic character, it's this direction is positive, this direction is positive. I can kind of see it. Oh, that's kind of cool. Same color blue, but it looks different. Anyways, back to back to this example. I can kind of see that here in the P block, but that would tell me that cesium and francium are like the best metals. Like, what's the best metal? What does it mean the best metal? The most conductive metal is silver, but carbon also conducts electricity and heat, and DNA molecule, which is made of all nonmetals, also conducts electricity. So, I mean, conducting electricity does not mean metallic. So, and does something that be having a high melting point, does that make it a good metal? Well, not at all. Thorium has a really high melting point, but boron has an even higher melting point. Mercury has a very low melting point. Helium may not be a liquid at all. It might just be a gas. I mean, so there's nothing here to put that trend with anything. Where it could happen, though, if you look in this direction, the metallic-like behavior does increase in that direction in the P block, like I said. But for me, myself, I think that's a stupid trend. So because it's not, I mean, like first ionization energy, yes, definitely. Helium, highest first ionization energy. That makes sense. Size, cesium and francium. Francium, if it existed longer than a few seconds, would be the biggest atom. Or while it exists, is the biggest atom. Right, but it doesn't really work for metallic character. Okay, and this stuff, actually I'm a reviewer for the next edition of the textbook, and they even take this part out, so I'm going to go ahead and preemptively and not teach about it. This is just chemical properties of the alkalis, but I've already told you everything that you already know about them. Alkalis +1, they are very reactive. So on, halogens make salt, noble gases don't react. So in that regards, I'm inclined to stop here. So anybody have any questions about anything? Crazy, huh? Chapter in a day. So only got 3 more to go. It's kind of scary, huh? But yeah, so I think that's a good place to stop.